Good evening, my fellow scientists. It is Tuesday, December 26th, 2017. Happy Christmas to those of you who celebrate it. I am working on the iron battery today, and I have a bit of a walkthrough on the charge-discharge cycles I have been doing. So let's go through that. So some time ago, I rigged up a standard galvanic cell with this chemistry just to kind of measure the typical cell voltage off of this system. And when you have iron dissolving on one side of the cell, you generate about 0.6 volts. That current is driven into iron 3 plus and reduces it to iron 2 plus. That's the catholyte, that's what's taking up those electrons. But the cell voltage is 0.6 volts, and we can abbreviate the cell as just the schematic symbol for a cell there, and say that cell has a nominal voltage of 0.6 volts. So if we want to charge the cell, we need to apply more than 0.6 volts. So we apply a larger potential, call it 0.8 volts, and that's going to drive positive current into the battery. Just by the way we have it hooked up and defined, that's going to be positive current. And we can measure that with a little ammeter. So if that's charging, what about discharging? For a discharge, you're going to run current through a resistor. We're going to define that as negative current. When negative current flows through that resistor, you get some voltage on that resistor. And using a potentiostat, we can control the resistance to get whatever voltage we want. In this case, we're going to regulate that resistor to get 0.05 volts. The cell itself is still nominally, ideally, a 0.6 volt cell. So where's the rest of the voltage? Well, there's internal resistance. That is to say that inside that cell, due to the need to reorganize the ions and so forth, there's some resistance built in, and that takes up the rest of the potential. So I set this cell up to charge and discharge. I charged at 0.8 volts and then discharge at 50 millivolts and repeat over and over again. And this is the curve you get. You can see at the very beginning, right there at 0 minutes, there's almost zero current. I'm applying 0.8 volts, but nothing is happening because the cell is already fully charged. At that point, I transition to the 0.05 volts. You get negative current. I get a lot of negative current, 25 milliamps. For this size of a battery, that's pretty good. And then it repeats over and over. And you can see there's a lot of drift. So clearly the chemistry is changing. Is that because I'm having a lower actual ideal cell potential? That is to say the chemistry is changing? Or am I increasing my internal resistance because the oxide layers are building up or my membrane is degrading? I'm not sure yet, but we're going to keep an eye on this change as we iterate the next part of the battery, because I suspect what's happening is there are irreversible chemistry happening between the iron and the EDTA, and if we take the EDTA out, we should fix this. So having charged and discharged the iron EDTA battery a number of times now, I'm pretty sure that that EDTA chemistry is going to cause a bit of problem, that there's some irreversible, non-rechargeable sort of chemistry going on when the oxidizing iron complexes with EDTA. I just don't think it comes back out well. So having established that hypothesis, next we're going to test that by going back to the iron chloride cell. That's the only thing I've really changed between the iron chloride last time that seemed to be quite reversible and the iron EDTA that seems to be irreversible. We'll check that, make sure it's not something about the construction of the cell. Once we've confirmed that, we can start playing with some other really simple ligands to see if we can stabilize the cell and make it more accessible. Iron chloride is super cheap. We just need to get the stability and pH at optimal for home consumption. So if you like that kind of thing, tune in Monday through Friday. We update once a week on progress on the iron battery, as well as science news and random interesting things I find cool in chemistry.